All right. Well, it looks like our next speaker is due to come on in just about 60 seconds. So we have to do sort of a quick intro. Brian, you want to jump in there and introduce our next amazing speaker?
Yes, we can. I think it's a perfect segue because Shipley was talking about code signing a little bit, and our next speaker is going to be talking about code signing and how you can still get hacked after signing your software, right? So it's perfect for that. But to help set it up, we have joining us to speak on this is Gal, who has 10 years of software development and cybersecurity experience. Gal's early career included software development for the Israel Defense Forces, Unit Matzav, and followed by roles as a Linux kernel engineer at Volumes, and a technical lead at Infinidat. This is like a tongue twister for me, trying to make sure I'm pronouncing these things well. Gal also came to Legit Security, where he's at now, as a security researcher and subject matter expert on software supply chain security. And with that, let's bring Gal on to start our next session.
Welcome,
Hi,
Gal.
everyone. Hi.
Welcome.
Great to see you. Thanks for coming
Can
by.
we all agree that? Can we all
Thank you
agree that
for
Legit
having me.
Security is an awesome name?
Yes.
Thanks. Yeah, I love it too.
Now, will somebody come up with illegit security to counter that?
That would be a problem. Yeah.
Nice.
That's their dark web sister company.
Well, Gal, we're all looking forward to your talk. So without further ado, the floor is yours, good sir.
Perfect. Thank you. So, yeah, cool. I just start the presentation. Cool. So, yeah, I'm Gal, and in Legit, I actually research supply chain security, CI/CD, pipelines, and other SDLC assets, and looking for risks. And now we're going to talk about artifact poisoning in Docker registries, and we'll see why you can still get hacked even after you sign your software artifacts. Now, we'll start with understanding why the registry is actually the weakest link in the pipeline, and we'll see how would artifact poisoning go in the process. Then we'll see artifact signing as a measure to protect against it, and we'll see how to do it right, which is not so trivial as one would expect. Then we'll see the community adoption for the solution and the next steps for you to take. To start, let's meet the supply chain of Alice's restaurant. So in the kitchen, we have the cooks using different ingredients. And when they finish preparing the dish, they can pass it to the Alice, the chef, which checks the dishes for food quality issues or food poisoning. And if everything is fine, Alice can put the pasta on the serving bar where it waits. And it waits for the waiter to pick it up and deliver it to the customer, Bob. Now, the waiter just takes it off the serving bar and delivers it to Bob. And when Mallory, our malicious actor, decides to poison Bob, we need to ask ourselves, where would Mallory decide to inject poison? So the kitchen is full of the cooks and Alice, and they check for the quality. And the natural place for Mallory to go would be the serving bar when no one is looking at the pasta. And now when the pasta is poisoned, the waiter just picks it up and delivers it to Bob. And that's a bit of a problem. And now, like every other business owner in 2022, Alice decides to go to the cloud, and Alice's restaurant is going digital. And now instead of a kitchen, we have the SEM, and we have different branches. And when they are ready to merge, they go into the main branch. And in this process, we have code reviews, SAS, Dust, and other tests to make sure that the quality of the code is fine and there are no vulnerabilities. And only if everything checks out, then we can prepare the Docker and push it to the registry. In the registry, we store the image, and it waits for the CD to pick it up, to pull it actually, and to deliver it to production. It could be either the cluster or a cloud environment or whatever environment you have. And once again, the natural place to inject the poison would be in the registry after all the checks are already passed. And this time, the attack would be to override the tag to point to a different image, a malicious one, that the attacker pushes. And then, once again, the CD would just pull the image off the registry and deliver it directly to production. Now, we have a problem, and let's just see how that kind of process would look like from the code perspective. So we have the original Dockerfile that Alice uses, which is a simple hello-world application. On the other end, the malicious Dockerfile is having some malicious code running inside it. And actually, the publishing process would be similar. In both cases, it would be a simple build where we also tag the image, in this case, hello world and v1.0, and then we push the image using the tag. And on the other end, on the CD, we'll simply use the image and tag to specify the image and deploy it. Now that we understand that process, let's ask ourselves, how could a malicious actor actually get access to the registry? So it could be more trivial than one would imagine. It could be because of misconfigured systems, such as a registry with anonymous access allowed, or just an unpatched version. Or otherwise, it could be because of credentials compromise, meaning credentials leak or secrets in code. Or otherwise, it could be via social engineering, phishing, or an internal threat. And now that we know how to get to the registry, let's ask ourselves how to protect against the artifact poisoning. So for Alex and Bob, the way to do it, which are actually the CI and the CD, would be to sign the image in the CI, then upload that signature to the registry. And in the CD, we would verify the signature, and only if the signature is valid and matches the image, we would deploy the image. Now, back to the pipeline, once again, we push the image, then we sign it, and only after signing it, and the deployer would be able to verify the image and make sure that the signature matches. And if everything checks out, only then we can deploy to production. How would we do it? So as mentioned in the previous talk, there is Sigstore to the rescue. We can use projects such as Sigstore, which is actually probably the most popular container signing project, and it is open source, and we can use it to both sign and verify the image. And when it comes to code, now on top of the build and push, we also have cosign sign using the private key and specifying the image and the tag just like before. And on the other end, we have cosign verify using the public key to verify the image. And only if the verification succeeds, we would proceed to deployment. Now, the thing is that there's still a problem here. And to understand the problem, we need to recall what is a tag. So a tag is a label that is used to describe the image, and is actually a mutable reference to the image. What that means is that anyone with write access to the registry can override any tag and make it point to any image, in our case, a malicious one. On the other hand, tags are what everyone loves to use. It is handy, it is descriptive, it is very useful, and we do want to use tags. It is a convenient way to work with Docker images. Now, unfortunately, it is also the reason that this scheme is compromised. Tags open the door for the following race condition. Okay, so what is the race condition? We have Mallory, the malicious actor. Now, instead of pushing it once, Mallory uses a simple while loop, and Mallory pushes the image continuously. On the other end, in the CI, Alice would simply, just like we've seen before, would push the image once and then go and sign the image. Now, because Mallory continuously pushes the image, actually what would happen is that when we sign the image, we would sign the malicious one, which is pushed after the original one. So let's see how the race goes. First, we have Alice pushing the image like before. Then Mallory pushes the malicious one and overrides the tag to point to the malicious image. Now, when Alice signs the image, or in our case, the CI, obviously, then we sign the malicious image instead of the original one. When we continue to the CD and try to verify the image, we will see that the signature is valid. We actually sign it using the valid private key. Now, because of that, we would continue and actually run the malicious image in production. So we've just lost the race. And to understand how to deal with that problem and how to solve it, we need to now recall what is a digest. So a digest is an immutable hash value, and it corresponds to the content of the image. So every image has a single hash value corresponding to it, and this digest, hash value is a digest, so it is associated to this specific image. Now, the problem with digests is that they are long, as you can see below, and they are not handy, they don't describe the image, and they're hard to move from place to place, and no one would want to specify them manually in different parts of the pipeline. So hopefully we can find a solution to use digest, but not to specify them manually. And the reason we would want to use digest is because this way we can pin the specific version of the image that we want to use, meaning we can use our original image and not being in doubt about whether the tag is now overridden by the malicious one. And back to the code, now instead of just pushing the image and forget about it, we also take the output of the Docker push command, and this output also contains the digest of the freshly pushed image. Now, from that output, we would extract the digest, and now when we want to sign the image, we would use the digest to specify the image, meaning that we can be certain that the image that we sign is actually the original one and not the one that might be overridden later. On the other end of the process, we have the verify command, and from that output, we can also extract once again the digest. And when we deploy the image, we would use the digest to specify which image we want to deploy. Now you can notice that when we verify it, we actually use the tag, but then we know that the image that we verified is the one that we got in the output, and this is the one that we get in the digest. Now, just something to notice here is that in no point in the process, neither in the signing or the verification, we didn't actually specify the digest manually. We still use tags like modern pipelines, but we still got the digest when we needed to sign the image and to actually deploy it. This way we get the best from both worlds. And when we go back to the pipeline to see how would it go, so once again, Alice pushes the image, and now we can see that it also has a digest associated to it. And now, once again, Mallory pushes the malicious image and makes the tag to point to the malicious image. But the difference here is that now that we sign the image, we actually signed the original image because we specify it using the digest and not the tag. And what it means is that when we go to the CD and we need to verify the image and we do it using the tag, as we've seen, we'll see that there is no matching signature to that image because we didn't sign the malicious image, we only signed the original one. Now, with that knowledge, we can actually abort the deployment and prevent the malicious code from running in production. Okay, so let's have just a quick summary of the different steps we went through. At first, we had no signing at all, meaning we could have artifact poisoning pretty easily. Then we used tags, which is probably the most intuitive way to use Dockers, and we used it to sign the image. But unfortunately, as we've seen, it enables actually the malicious actor to use the race condition to still poison the artifact. Finally, we use digest, and this way we just shut the door on Mallory, and no artifact poisoning is allowed here. Okay, so when we discovered this problem, we then went to the community and wanted to make sure that no one is impacted by that race condition. So first there is the Sigstore project, and we went and reported the case to the project, actually in the Slack channel. And now when users use cosign to sign images using tags, it would warn them. And after a compatibility period, the support for container signing using tags would be completely removed from cosign. In addition, we went to the Go Releaser project, and we contributed a patch that makes sure to output the digest of generated Docker images, which means that now users can actually take the digest and use it to sign the images that they generate. And finally, we went to the Salsa project and made sure to update the documentation to also use the digest from the Go Releaser process and use it for provenance generation in Salsa. Now, in addition to these two projects, we also opened the issues for the Docker project and to make sure that this kind of race condition does not happen with Docker Trust, meaning that if anyone wants to sign a remote tag, it would not be allowed. And also with Notary project, which is pretty similar to SigStore in many aspects. We also opened the issue and made sure not only to prevent and warn users about text, but also to update the documentation so users can be aware of the problem. Finally, what should you do about it? So first, you need to keep a tight grip on your secrets and your access keys and to protect your registries. So the prerequisites that we had for that attack won't be met. But still, even if you do that, things might go wrong and secrets might leak. So make sure to sign and to verify your artifacts in your pipelines, and make sure to do that correctly using digests and not tags. And finally, I encourage you to be more aware of this kind of software supply chain security issues and risks. And you can do it by listening to talks like and going to conferences like this one, or reading more. You can read more in our blog, and there is a lot of content in this area these days. And finally, I want to thank you for listening, and I want to thank again DevSecOn for hosting me here, and I hope you enjoyed it, and let me know if you have questions.
Excellent talk. Thank you, Gal.
Thank you.
Yeah,
I
Great
need to get
talk.
that applause sound effect going.
It's scary to think of all the different ways people can basically trick you into deploying malicious images. It's pretty insane.
Right.
Do we have any? Is there any occurrences that we know of where somebody accidentally signed a poison version and it got out into the wild the way that you described?
No, so actually we haven't found such cases in the wild. Obviously, there are the infamous Codecov attack where artifact poisoning in registries took place, but we don't know of this attack being taken advantage of.
Got it. Yeah.
Yeah, it's
Well,
a
very
scary
cool.
topic, especially since you can really trick people into signing the malicious images as well, which is, I think, something people don't expect. It always seems to me, so maybe, I know you have a lot of background in this, but it always seems interesting when you're talking about cryptographically signing things in general, because I think most software developers view a cryptographic signature as essentially being infallible, you know? And I think the
Right.
reality is there's so many different ways to abuse that or trick it. You know, both in terms of code
Right.
signing, even when you're using GPG keys on GitHub, to everything like artifact signing. It's just scary out there.
Totally. In my opinion, actually, when you find a malicious image, it's much worse, because when you find things, as you said, one would trust it much more than an unsigned image, and then you just deploy it directly to production and do much more dangerous stuff with it. So yeah.
And there's
Are
no
you-
possibility for somebody to fake the digest, right? It literally has to
Right.
have the same exact contents of
Right. So using like SHA-256,
Yeah.
so you get like 2 to the 1 to 128. So it's, I mean, it's practically impossible.
Okay.
unless they're using MD5 with tons of collisions and stuff, and just
Right.
causing all sorts of havoc everywhere. Yeah.
Yeah.
I use base64 encoding. That seems to be the best way to go about it, right?
I heard, could you comment on this? I heard ROT 13 was the new best standard for modern encryption. Any commentary there? Please don't use ROT 13.
Some quick
Awesome.
quick comments from the chat. I see Gabriel over on Hopin says props on the graphics used, changes from the usual Al/Bob graphs on Wiki. So there you go, thumbs up on that. And then somebody over on YouTube by the name of Micah Silverman says great talk, Gal. So
Thanks.
there you go. Thanks so much, Gal. That was excellent.
Yeah,
Cool,
thanks
guys.
for joining
Thank
us.
you very much for having me.
All right. See ya.
Okay. Bye-bye.
All right. So, Micah, do you want to introduce our next speaker?